Welcome to SDN Tech Networking Podcast, world's first human-curated AI podcast where we break down complex topics.
Welcome to The Deep Dive, the show that pulls the most critical knowledge out of complex technical docs and puts it right into your hands. Today, we are jumping headfirst into a conceptual primer on SONiC, that's software for open networking in the cloud.
Yeah, this is a really big topic for any network engineer who's watching how data centers are evolving. If you're coming from a world of, traditional monolithic network operating systems, this deep dive is for you. We're going to break down the why behind its design.
Exactly. Our whole goal here is to give that architectural primer. We've gone through the in-depth documentation, the engineering talks, all of that. And we're focused on the core components, the flow of information. Not, a bunch of command line stuff you can't see.
It's about getting the blueprint of the engine. We're going to look at how SONiC really separates concerns, how its state management works, and the really critical hardware abstraction layer.
Those three things, that really defines modern hyperscale networking. So let's just set the scene. What exactly is SONiC? And why did it go from just being an internal Microsoft project to this huge thing in the industry?
Well, at its core, SONiC is an open-source network operating system, NS, built on Linux. It was created by engineers at Microsoft who were just dealing with the immense complexity of their global data centers. And then they contributed it to the Open Compute Project, the OCP.
And its whole rise is basically a reaction against the old way of doing things, right? The vertically integrated, closed systems.
Totally. When you talk about the limitations of those old systems, you're talking about vendor lock-in. You bought Switch Model A, you got OSA, and that was it. If you needed a new feature, you just had to wait.
You were on their roadmap, not yours.
Exactly. So the value proposition for you as a network professional is just radical flexibility. And it's important to say this is production-hardened stuff. It supports all the features you'd expect, BGP, RDMA, all the advanced data center tech. But the real power is in the choice it gives you.
The choice of hardware is the obvious one. It runs on a bunch of different ASICs, a bunch of different chips. But what about the software choice? What does an open source NAS really give an engineer there?
It gives you the flexibility to mix and match software features. In a monolithic OS, everything, routing, monitoring, LLDP, it's all tightly coupled together. With SONiC, you can pick the best container for a specific job, or even build your own and just deploy it. It completely decouples the software features from the hardware underneath.
So it's like instead of buying a fully assembled car off the lot, you're buying the chassis and the engine, and then you get to decide which navigation system, which stereo, which seats you want to bolt onto it.
That's a perfect analogy. And if your GPS system crashes, the engine keeps running. You gain that software independence, and you can tailor your network to your exact needs.
Okay, that idea of separation, of things not breaking each other, that leads us right into the architecture. The big differentiator for SONiC is that it's almost entirely built on containers. So walk us through that. Why is containerization so fundamental?
Okay, so a traditional NOS runs everything as, one big process in a single OS image. If one small part of that has a major failure, it can destabilize the whole switch. SONiC just flips that on its head. Every major network function, routing, monitoring, you name it, is isolated in its own Docker container.
So if I'm understanding this, the BGP routing protocol is running in container A, while the link layer discovery protocol, LLDP, is in container B. They're totally separate fault domains.
Precisely. And that means fault isolation and just a massive simplification of operations. If you need to upgrade your SNMP agent, you just restart the SNMP container. The rest of the switch doesn't even notice. If your BGP process fails, maybe there's a memory leak. The actual forwarding plane in the ASIC often just keeps on working.
Let's make that a bit more concrete.
Right.
In the routing container, you see these names like BGPD and Zebra. For an engineer who hasn't really worked with these Linux-based systems, what are those doing conceptually?
Yeah, good question. So BGPD is the daemon that's actually speaking the border gateway protocol. It's talking to your peers, learning routes. But the key part is Zebra. Think of Zebra as the manager, the routing information daemon. It collects all the routing information from BGPD and any other protocols you might run, decides on the best path, and then gets that info ready to be pushed down.
And the whole point of SONiC is that these really powerful, complex functions are all self-contained.
Exactly. And it's not just for networking protocols. Even system health is modular. You've got a container called PMON, the platform monitor. Inside that, you have little processes like censored, which is logging all the hardware temperatures and alerts, and fan control, which is actively managing fan speeds based on those temperatures. They're all separate from the actual traffic forwarding logic.
Which means you can debug or update them in isolation. Much lower risk.
Much lower risk.
Okay, this brings up the biggest conceptual question for me. If everything BGP, LLDP, SNMP, the platform monitor, is running in its own little sandbox, how do they synchronize? How do they all agree on what the switch is supposed to be doing?
That is the million-dollar question. And the answer is the database container. It runs a Redis server instance, and this isn't just for storage. It is the single source of truth. It's the high-speed communication backbone for the entire UNOS.
Okay, so why Redis? I mean, I know it's fast, it's in memory, key value. That seems like a good fit.
Speed is absolutely critical. Network states are constantly changing. Links go up and down, routes flap. You need that low latency read and write so applications can sync up in near real time. And within this one database container, the data is logically split into 3 key databases.
All right, let's break that down. First one, where does my configuration, the stuff I type in, where does that live?
That goes into the config.gb. Think of this as the database of intent. When an engineer makes a change through the CLI, or more likely in an automated setup, loads a config.json file, that's where the desired state is stored. It's the blueprint, what you want the switch to be.
Got it. Intent. So what about the applications themselves? Where does BGP write the routes it learns?
That goes into the APPLDB, the application database. This stores the operational state that's generated by all the running applications. So when BGP learns a new route from a peer, it writes that route, the next hop, all that data right into the APPLDB.
So config.gb is what should be, and APPLDB is what is happening right now. What's the third one for?
The third one is the stated DB. And this one is maybe the most critical for stability. It holds the system's resolved state. It's for managing dependencies between containers. So, for example, BGP needs an interface to be administratively up before it will try to form a peering. The BGP container checks the stated DB to confirm the interface's status is up before it even tries. It prevents all sorts of race conditions.
Okay, that's the glue that holds it all together. So we've gotten the config from the user into the database. The operational state is flowing between the containers. But none of that matters unless the physical switching ASIC is actually programmed to move packets. How do we get from a key value pair in Redis down to a command in the silicon?
That is the job of the Switch Abstraction Interface, or SAI, and its partner, the SyncD container. This layer is what makes hardware independence possible.
Define SAI for us. What is that?
SAI is an open-source, standardized C API. The simplest way to think of it is as a common language, a standard blueprint for all switch hardware. Before SAI, every chip vendor had their own proprietary way to be programmed. SAI was created within the OCP to provide one single, consistent way to program all the basic forwarding stuff, like creating a VLAN, adding a route, defining an ACL, no matter whose chip is in the box.
That sounds like a massive effort, building a universal driver for networking silicon.
It is, and it was a total game changer. But SAI is just the API definition. You need a process that actually uses it, and that's the job of SyncD.
So SyncD is the translator. It takes the software state and turns it into hardware action.
Precisely. SyncD is a dedicated container, and its only job is to watch the central database for changes that need to be pushed to the hardware. When it sees a new route appear in the APPLDB, SyncD reads it, translates it into the right SAI API call, and sends that call down to the next layer.
And because the hardware vendor provides their own SDK, their own library, that understands the SAI standard.
Right.
The high-level Sonic software doesn't have to know anything about the chip itself.
That's the magic right there. SyncD speaks SAI, and the vendor's SDK handles the low-level proprietary talk to the physical ASIC. That abstraction is why Sonic runs on so much different hardware. It shields the whole software stack from the silicon specifics.
Okay, let's pivot to the engineer on the keyboard, the person actually managing this thing day to day. We know the architecture is containerized, but what are the main ways they actually interact with it?
So even though the architecture is super modern, the main tool for troubleshooting is still the familiar command line, the CLI. And the Sonic CLI is organized very logically around two top-level commands. It separates viewing from configuring.
And that would be show and config.
Exactly. Show is your window into what's actually happening. Use it for status, debugging everything from show interfaces status to looking at BGP routes or checking show processes, CPU.
And config is where you make changes that will actually stick around after a reboot.
Yes, but here's a really important point for anyone coming from a traditional networking background. While the CLI is great for a quick check or a small change, in a hyperscale environment, you almost never use the CLI for provisioning.
Why is that? Automation.
100%. Sonic is designed from the ground up for automation. The preferred way to configure it, especially at scale, is by manipulating structured data. So engineers are really working with files like configdb.json. An automation system just pushes a new version of that file, it gets loaded into the configdb, and that triggers all the containers to update themselves.
That makes total sense. If you have 10,000 switches, you can't be SSHing into them one by one. You define the state you want in a file that can be version controlled and managed by a pipeline.
That's it. Whether you're configuring interfaces, port channels, VXLAN, ACLs, it's all there. But the conceptual takeaway is that you define your network as data objects that land in the config.gb. It's truly top-down, programmable infrastructure.
This has been a really great walkthrough of the architecture. So to sum it up, for the network engineer trying to get their head around Sonic, it's defined by these isolated resilient containers. State is synchronized through a central, super-fast Redis database. And the whole software stack is separated from the hardware by that standardized switch abstraction interface, SAI.
Those are the foundational pillars, absolutely. But if you connect that modularity to what's happening with the newest generation of programmable ASICs, Sonic's architecture gives engineers something way more profound than just flexibility. It gives you deep control over the hardware pipeline itself.
Okay, that's where the real customization comes in. How does that actually work?
Well, because you have this clean separation between the applications and the hardware, you can select and apply a specialized hardware profile. Often, it's just a simple parameter in the configdb.json, something like P4 profile. And that profile tells the ASIC how to allocate its own finite, very valuable internal resources.
Whoa. So you're not just configuring software features, you're telling the actual silicon how to organize its own memory and tables based on its role in the network.
Precisely. If your switch is a leaf, you might apply a profile that prioritizes L2 and L3 forwarding table space. If it's a spine switch that's doing a lot of heavy tunneling, you can adjust the profile to allocate more table space for MPLS or VXLAN. This ability to tune the ASIC's resource allocation with just a software parameter managed through the Sonic framework, that is the ultimate promise here. It turns commodity hardware into a custom-built solution.
That level of granular control is a huge shift, moving way beyond the old fixed function boxes. A fantastic explanation of the system that's really underpinning the modern cloud. If you want to dive deeper, we'd really recommend looking into documentation on pipeline resource management. See how those config entries flow through the databases we talked about. We'll catch you on the next deep dive.